This is the Skogafoss waterfall in Iceland. Every day here, hundreds of millions of litres of water tumble down towards the sea. More than 70% of Earth's surface is covered with water. But that wasn't always the case.
Early in our planet's history, when the surface was far too hot for liquid water, this planet was shrouded in a thick atmosphere of carbon dioxide and water. And all you'd have seen from space is the white cloud tops. But as the planet cooled, the rains began, and a deluge shifted most of that water from the atmosphere to the oceans. And then when the rain finished and the clouds cleared, the liquid of our blue planet was on show to the universe for the first time.
Ever since, the sheer physical power of water has been carving and shaping the surface of our planet. And crucially for our story, all this water has had huge consequences for the Earth's temperature. To understand why, we need to delve into the strange world of water at the molecular scale. And that journey begins with a chance discovery that revealed for the first time what water is actually made of. In 1766, a reclusive scientist, Henry Cavendish, added various metals to a liquid called spirits of salt, now known as hydrochloric acid.
And what he saw was something that he called inflammable air, but today we know as hydrogen. And Cavendish was the first person to recognise its significance and to do experiments on it to test its properties.
Cavendish collected the gas given off by his experiment. When he had enough, he took a flaming splint and put it next to the opening. With explosive results. Afterwards, Cavendish noticed something intriguing.
On the inside of the glass vessel, there were tiny droplets of a clear liquid. And he wondered what that was, he tasted it, he smelt it, and he came to the conclusion that it was water. And so Cavendish was the first person to realise that water was a combination of hydrogen and oxygen. And today we know that the chemical formula is H2O, 2 hydrogens and 1 oxygen. And that sounds beautifully simple, but still, water is one of the most fascinating molecules we know of.
The molecular structure of water is the key to why Earth's temperature is warmer than you might expect. Yet it's in a cold place where we can begin to understand just why that is. This is Jökulsárlón Lagoon in Iceland.
Isn't this all stunning? All these bits of glacier that have just fallen off from up there. We take scenes like this for granted. This is our impression of the Arctic and the Antarctic, floating icebergs. But from a material science point of view, that thing is really weird because it's floating with almost everything else. When you cool things down and freeze them, the solid will sink to the bottom of the liquid. But water is different. It floats.
As a liquid, the molecules of water are constantly sliding past each other, always on the move. But as it freezes, their positions become fixed in a regular hexagonal lattice. Ice floats because the molecules in the lattice are taking up more space than in the liquid, which makes ice less dense than water. This happens because of the forces holding the molecules in position. Something that's more easily seen with water in its liquid state.
I've got some plastic pipe here and a proper Icelandic woolly jumper because it's made of wool and therefore it's good at charging up the plastic. So this pipe now has an electric charge, and what I'm going to do is put it near a stream of water, and you can see that it bends the stream really strongly. And all the water's doing is falling, but it's being pulled towards the electric field.
The reason for this phenomenon lies within the water molecules themselves.
This is the water molecule, so we've got two H's, that's the H2, and then O is the oxygen at the top. And the charge on the molecule isn't evenly distributed, so it's more positive around here and it's more negative up there. So when the stream of water comes down, it's got all these molecules moving around inside it. When you bring the electrical field close, some of those molecules will flip around so that their opposite charge is attracted in to the electric field, so the whole stream of water moves. And it's such a simple demo, but it shows you that the water molecule itself has uneven charge distribution.
And this has a huge effect on how water behaves. Within the liquid, the negatively charged oxygen atom from one molecule is pulled towards the positively charged hydrogen atoms of another, creating a strong attraction known as a hydrogen bond. And it's this bond that explains water's role in distributing heat around the planet. Hydrogen bonds are so strong that it takes a lot of energy to break them. And that means that the water in the Earth's oceans can absorb a huge amount of heat energy from the sun without changing from a liquid to a gas. The oceans act like a huge store of energy. And as they move, they distribute heat from the equator to cooler latitudes north and south.
This is a material with a very long name. It's yttrium barium copper oxide. And it doesn't look like very much. There's very strong magnets here, and it's not responding to them. It doesn't conduct electricity. Doesn't seem very interesting. But when you cool it down, it changes completely.
Using liquid nitrogen, we're reducing the temperature of the disk to minus 196 degrees Celsius. And now, when I bring it close to the magnets, something unexpected happens.
It's levitating. And it will scoot around on the little track here for quite a while. So something's changed. We cooled it down. The behaviour changed completely.
And that's because cold has altered the material at the atomic scale. Materials conduct electricity when electrons travel through them. But the atoms in a conductor are an obstacle to the flow of electrons, because as electrons bump into them, they lose energy. At extremely low temperatures, the electrons can team up into pairs. And then, the attraction between the electron pairs helps them navigate through the atoms far more easily. So when I bring the disk close to the magnetic track, a strong electric current begins to flow in the disk. This in turn generates its own magnetic field. The magnets in the track and the disk repel each other, and so the disk levitates.
This is an example of superconductivity. Once it's cooled down below the critical temperature, the properties of the material change. It becomes able to conduct electrical currents without any resistance. And that also changes how it responds to magnets.
The peculiar electromagnetic properties of supercooled materials have given us a powerful new tool in engineering and medicine. Some countries already use a supersized version of this magnetic levitation effect in their high-speed rail systems. Having no contact with the track, trains run faster and more smoothly and efficiently. And inside MRI scanners, liquid helium supercools massive coils of copper wire to a temperature of minus 269 degrees Celsius. At this extreme cold, an electric current can flow with almost zero resistance, which helps generate the powerful and stable magnetic field that the MRI machine needs. The extraordinary discoveries we've made at extremely low temperatures are now driving one of the biggest scientific quests of the modern age. How cold is it possible to go? And how do we get there?
We know that as you cool materials down, they tend to turn into liquids and then solids. But actually, the question of how cold you could make something started with gases. And this was the kind of experiment that was used. What I've got here are 4 beakers, each of which is at a different temperature.
They range from -5 to 50 degrees Celsius. Into each, we're placing a syringe containing 15 millilitres of air at room temperature. This air will heat up or cool down until it's at the same temperature as what's in the beaker.
So much science is about waiting. This is one of those experiments.
But it's not the change in temperature that's interesting here, it's something else. After 5 minutes, the air that's heated to 50 degrees has expanded from 15 to 16 millilitres, while the air that's cooled to -5 has reduced to 14 millilitres. In other words, there's a direct relationship between the temperature of a gas and its volume.
So the first scientists who saw this kind of relationship did something very straightforward. They plotted a graph that showed temperature against volume. And at the higher temperatures, the volume was higher, and as you go down to the lower and lower and lower temperatures, the volume decreases. And then there's a question, because at some point, even though they couldn't see it, if that line kept going, it was going to pass through 0 volume. And at that point, and past that point, what happens to the temperature? What does it mean? And that was the first hint that there might be a limit on just how cold you can go.
This observation led to a concept known as absolute zero, the theoretical limit of cold.
And now we know exactly what it is. On the Celsius scale, it's -273.15, a fantastically low temperature, but below that, there's nowhere to go. That's the coldest you can get.
And it remains a theoretical point on the temperature scale. The Boomerang Nebula, 5,000 light-years away from Earth, is the coldest place we know of in nature. It's a star in the late stages of its life that's shedding huge plumes of gas. As this gas expands rapidly into the void of interstellar space, it loses energy quickly, resulting in its unusually low temperature of -272 degrees Celsius. But even this is 1 whole degree warmer than absolute zero. Though we've yet to find absolute zero in the far reaches of the universe, we're trying to create it ourselves, much closer to home. At Imperial College London, Professor Ed Hines and his team are working at the very limits of the ultra-cold, within fractions of a degree of absolute zero. It promises to open up a whole new world of physics, which could revolutionise our future. The stuff they're cooling here is tiny clouds of molecules. Chilling them to absolute zero requires 2 phases of cooling. First, using liquid helium, they take them down to within 4 degrees of absolute zero. But it's these last few degrees that pose the problem.
There are ways to make helium a bit colder, but to get to the millionths of a degree, there is no fluid that you can use. So instead, we use light. By scattering the light, the molecules will get colder.
Even at this temperature, the molecules still have some movement. Photons in the laser light collide with the slowly moving molecules, and in that instant, what little momentum they have is transferred to the photons. photons are scattered. But the molecules slow down and so get even colder. By using an array of different colours of laser light in just the right order, Ed and his team can reach temperatures within a few millionths of a degree of absolute zero. At these incredibly low temperatures, materials begin to behave differently at the subatomic or quantum level. In this quantum state, they exhibit strange properties, which might lead to a new type of computer. A normal computer bit can only represent a 0 or a 1, but these quantum materials can be 0 and 1 at the same time. Link these multitasking bits together and they can do vast numbers of calculations simultaneously, far faster than any conventional computer chip.
This opens up the possibility of quantum computing, quantum sensing, quantum cryptography. These are all ways of doing useful things, but much better.
I've travelled to the north of England to meet a bunch of enthusiasts with a head for heights. Harry Stringer is from the Pennine Region Balloon Association. He's been flying hot air balloons for over 25 years.
So where are we going today?
Well, we'll clear the treetops here.
That sounds like a
and
good
then,
start.
Yeah, and then we'll go up to about 1,000 feet.
Okay.
Hands on!
The very first hot air balloon, launched in 1783, was the brainchild of two brothers called Joseph and Etienne Montgolfier.
Oh, for free!
OK, we're away, John.
One story goes that Joseph had been staring into his fireplace one evening when he had the idea of filling a paper bag with hot air. On letting the bag go, he observed that it began to rise. And this encouraged the brothers to repeat the experiment, but this time with a much larger, purpose-built balloon. And the really ingenious thing about balloons is how they exploit a crucial property of hot gases.
The mechanism of these is beautifully simple. There's a bag above me filled with hot air. What the burner does is allows the balloonist to play around with the density of the air by controlling its temperature. And as the air inside there is heated up, and it could get up to 100 degrees Celsius, it expands.
As the air expands, its individual molecules push outwards, making the air inside the balloon less dense.
Gravity is pulling everything I can see down to the ground. But because the air inside the balloon is less dense than the air around it, everything around us is being pulled down more, so it's squeezing the less dense balloon upwards. And so balloonists are floating on top of the denser air around them.
But temperature doesn't just enable a balloon to rise, it also controls how it falls.
So how do you make us come down?
We'll have a parachute vent. It's massive, you can see it. I could pull this red line,
Yep.
and it will open the valve, and then I just close it, and the gulp of hot air loss will cause the balloon to descend. We are safe.
Can we stand up now?
We can. We can.
The discovery that heating up air could make it expand enough to lift people into the skies was a milestone in human innovation. And And it wasn't long before we began to put that very same heat energy to a much more practical purpose. It was something that emerged from a very 18th century problem. 300 years ago, mine owners in Britain were facing a serious crisis. Since many ore deposits sat well below the water table, they were finding that their mines could only go as deep as the drainage technology at the time allowed, resulting in many mines going out of business. What was needed was a way to haul all that water up to the surface, so the miners could get to the ore below. And in 1712, an ironmonger called Thomas Newcomen hit upon the answer with the world's first commercial steam engine. And it worked by harnessing the immense energy contained within hot steam.
The principle behind Newcomen's engine is exactly the same one that Otto von Guericke had demonstrated. And that's just how hard air pressure can push, especially when there's a vacuum on the other side. I've got a plastic bottle here with some water in the bottom, and I'm going to put it in the microwave to heat the water up. What's happening inside the microwave is that the water molecules are being given energy, and they're not just heating up, but some of them are turning into a gas, into steam. And that steam is starting to fill up the bottle. And it's what happens next that's important. Tip it into this water here. And you can see that what happened is that the bottle has been crushed and it's now full of water. And the reason for that is that as it filled up with steam, the air was pushed out. And then when I cooled the steam down, it condensed from a gas back into a liquid, which takes up much less space. And so there was a partial vacuum left in the bottle. And so there was all the air pressure pushing in, nothing pushing back, and the bottle was crushed. And this is the principle that Newcomen used to drive his engine.
At the heart of Newcomen's engine lay a large metal cylinder housing a piston and filled with hot steam. Cooling this steam with water simultaneously created a vacuum and caused the weight of the atmosphere to push down on the piston, driving the engine. The cylinder was then refilled with hot steam and the cycle repeated. Soon, Newcomen's steam engines were popping up all over Britain. Each one a symbol of heat's ability to perform useful work. But Newcomen's design had one major weakness. It was hugely inefficient. Of all the energy in the coal that it consumed, only 1 to 2% was converted into useful mechanical work. The mystery was why. Where was all that heat energy going? And what could be done to retrieve it? To discover the answer, we've come to Cold Harbour Mill in Devon. Originally built in 1797, it's one of the oldest steam-powered woolen mills left in Britain.
OK, it's all right, you won't kill anybody with the other end.
John Jasper runs the mill's giant steam engine.
Right. That's good.
Like that?
You are a natural. Right, yeah?
OK.
Like so.
Yes.
Just bring it back in. Don't worry.
So tell me about these boilers.
This is a Lancashire boiler. It holds 20,000 gallons of water. Above that water level, you have steam. You get a bit of steam.
Right. So it's basically a sort of steam kettle. So these bits are the heating elements. Effectively, you're shoveling
That's
fire
right.
into the heating element.
That's it.
And then all of this is the kettle, which is full of water.
That's right.
But instead of coming out of the spout,
Yes.
it goes to a steam engine.
No, it
Just
takes a little longer to get to the boil.
better do some more shoveling then.
Yeah.